All right, so we already did day one. It is time for day two. So day one, we learned how to make the hero blink. And that's pretty much it. So, day two, re-edit. Oh, looks like we're gonna get into stuff. This is pretty exciting.
Greetings from Rescue Shuttle Control. Our telemetry indicates that you succeeded in starting up your hero controller.
He's just
You're ready to start working with it. That's great news. That's the first step in getting your shuttlecraft functional and ready to get you home.
We already made the light blink.
One of the first things that you're going to need to do
it now looks like we might make
turn on the lights in your shuttle,
an external light blink.
How to control the various functions on board. Doing that is going to involve developing some knowledge both of analog circuits and of the digital computer control that's provided to you by your hero. So we're going to walk through the basic use and the basic concepts of both of these functions during today's session. And by the end of today's session, we hope you'll have the lights on.
Yay!
You'll notice that in addition to the hero device that you've got in your shuttle, which connects to your ship's computer through the USB cable, you have a white rectangular plastic board.
I do.
This thing called a breadboard. Its purpose is to allow you to quickly and easily assemble circuits from discrete components. And by discrete components, I mean things like what we have here: resistors, light-emitting diodes, wires. And we will discuss what those components are and how they're used very soon. But I first wanted to sort of show you the breadboard that we'll be using in addition to the hero controller. Now, let's back up for a moment and talk a little bit about circuits, analog circuits.
Okay.
A circuit is a path.
I did start learning this last year, or the year before last, when I wired up my flamingulas. Hi, buddy. Hi. Look who's here. You want a little play, Belle? Yeah? Would you like a treat? All right, ready? Beep, beep, beep. Good boy. Okay. That's all. So yeah, I did start learning this, but then I lost my excitement for it.
Multiple paths through which electricity can flow around in some sort of a controlled and closed loop. It's somewhat like water flowing around through pipes or hoses. Now, in order for a circuit to function, the circuit must be completed in a complete circuit. And that's rather similar to the idea that in order to get water to flow around in a hydraulic circuit, we need to make sure that all the water containing or water channeling devices are connected end to end. And so in order for water to flow around a circuit, it's not just sufficient to have a complete circuit, but we also have to have some pressure provided in order to make it move. The higher the pressure, the more water will move through the pipes per unit time, and so the greater the flow rate will be. However, at a given pressure, more water will flow through a larger diameter pipe and less water will flow through a smaller diameter pipe. And in our analogy to electric circuits, the voltage, or another word for voltage,
should I be taking notes?
That's provided, say, by a battery or a power.
I feel like I should be taking notes. I don't know if that'll help me, but I'm just gonna I'm grabbing an old notebook. Hey, what's the matter? What's going on with you, huh? What's the matter? It's my notebook. I'm taking notes. Yeah, beat it. Beat it, kid. You bother me. Don't look at me like that. Okay.
Power supply is similar to the water pressure in our water.
Wait.
In our analogy to electric circuits, the voltage, or another word for voltage is potential, that's provided, say, by a battery or a power supply, is similar to the water pressure in our water example. And similarly to the idea that some pipes have greater resistance to flow and some have less resistance to flow, depending upon how wide the pipe is, we have conductors of electricity that have greater resistance or less resistance. So we call a device like this one right here, it's designed to have a specific resistance to the flow of electricity, a resistor, logically enough. And so a high-value resistor with a large resistance would be similar to a pipe with a narrow diameter that restricts the flow of water.
That's so cute. Aww. All right. So yeah, resistor.
A low-value resistor would be analogous to a wide pipe with a low resistance to flow. Now, if we want less current to flow through a circuit, for example, we would naturally insert a resistor that had a high enough value of resistance to reduce the amount of current to an acceptable level. And we can figure out how much current will flow through a resistor by taking the voltage applied, that's like the pressure in water, and dividing that by the resistance. So, as an example, our hero,
I do remember this from
is able to supply for us
my previous
a
studies.
voltage of 5 volts. There's a slot right here, a pin on the hero that's labeled 5V. That corresponds to 5 volts. We also have here some resistors like this one.
Oh yeah.
Or the one that's currently connected to the breadboard right here, that has a resistance of 220 ohms. So if I want to send current through this resistor using my potential of 5 volts, the current that would flow would be 5 divided by 220. So if you calculate what that value is, 5 divided by 220 is 0.023 amperes. So that turns out, luckily for us, to be just about the right amount of current necessary to illuminate this device, which is a light-emitting diode. It's like a light bulb, but unlike an incandescent light bulb, it doesn't function by heating up. It functions by converting electrical energy into light. So we wouldn't want to send too much current through our LED, because if we did that, we might be at risk of burning it up. So knowing the proper value of resistance to put into our circuit to limit the amount of current is pretty important. So
I did learn this last time.
Something valuable that we've learned about these circuits, and one of the basic ideas that we'll want to understand in order to design it.
This is good. Like if this first day or two covers the stuff that I already know, it's good. It's like easing back in
our own circuits. But now, before we go any further with that, we have a little bit more to learn. We want to not only be able to put together an analog circuit and have current flow through it.
And just so you know, like the big concept stuff, that is like what I'm kind of after. Because when I did my project, my Flamingula project, like I was learning very specific things as I went, and so I'd like to have a more complete kind of top-down thing. I do really love Electro Boom. He's great.
The desired amount. But we also want to be able to control our circuit by giving instructions to the hero through our computer. Now, it turns out that by writing correctly constructed code, we can tell the hero how and when to apply voltages to certain places on the hero board and use that to, say, illuminate a light-emitting diode. Now, let's go ahead. We're going to talk about how to construct that code and how to command the hero in a moment. But first of all, let's talk a little bit more about connecting our circuit together and connecting it to the hero. One way to connect circuits together is with wires, like the wires that we have right here. But if we have to solder everything together permanently, this can be very tedious and time-consuming.
I like soldering,
and
though.
It's also inconvenient if we want to change our circuit. So, for example, if
that's
we want
true.
to
I did learn this.
And we have a new idea and we want to
the
try
hard
a
way
new design. So, the breadboard here is there to make this job much easier, because instead of having to permanently solder components together,
yeah, I get it.
we can just connect parts together end to end by pushing their ends into the holes on the breadboard. The pins of our components fit right into the holes of the breadboard. And the reason why that's helpful is that the breadboard provides electrical connections between holes in the same row. So, for example, all of the holes here in row 6 are connected together electrically, or all the holes in row 5. It turns out that we've also got connected holes in vertical lines as well. This red, and this blue vertical line are also connected. And although we won't use those today, we'll find that it'll be convenient for us in the future to be able to use both horizontally and the vertically connected rows of terminals. For now, though, what we're going to do is illustrate how we might use the breadboard and the 5 volts provided by the hero to illuminate a light bulb or a light-emitting diode. As I mentioned before, this light-emitting diode can emit light when current flows through it. And unlike an incandescent light bulb, a light-emitting diode only works properly when current flows in one particular direction. That is, in through the long prong and out through the short prong. A way of remembering that is that we need to connect the longer prong to the higher voltage. That would be to the 5 volt side. And then the shorter prong would go to the low voltage side, or 0 volts. So let's see if we can use the breadboard to connect this LED to a source of voltage and get it to illuminate. Now, as I mentioned before, there's a pin on the hero labeled 5V for 5 volts. So we're going to take a wire and connect it to that 5 volt pin, and then connect that wire in turn to a particular row here on the breadboard. In this particular case, I've chosen to connect it to row number 6. There's nothing important about that.
I just stick it in there?
Random.
Oh, I see.
Also connected to row 6 is one side of this resistor, this 220 ohm resistor. If I were to then connect another wire from here back to 0 volts, or ground.
Oops.
Ground is another shorthand name for 0 volts in this circuit. The row here on the breadboard, in this particular case, I've chosen to connect it to row number 6. There's nothing important about that. Just pick that at random. Also connected to row 6 is one side of this resistor, this 220 ohm resistor.
Oh, right.
If I were to then connect another wire from here.
All right, I've got my 220 ohm resistor. So I put one side of it into 6. Does it matter where I put the other side?
Back to 0 volts, or ground. Ground is another shorthand name for 0 volts in this, about that. 4. There is a pin on the Hero labeled 5V for 5 volts. So we're going to take a wire and connect it to that 5 volt pin, and then connect that wire in turn to a particular row here on the breadboard. In this particular case, I've chosen to connect it to row number 6. There's nothing important about that, just pick that at random. Also connected to row 6 is one side of this resistor, this 220 ohm resistor. If I were to then connect another wire from here back to 0 volts, or ground, ground is another shorthand name for 0 volts in this circuit, then I would have current flowing through the resistor in a circuit.
Oh.
That wouldn't be too useful because the current really wouldn't be doing anything. So rather than simply sending a wire back to ground here, I'm going to send the current through the LED and see if we can get the LED to light. So let's connect the long end of the LED to row 10, like so. And it just so happens that the short end of the LED, where the current will be flowing out, is connected to row 11. So if I take one more wire and connect that to row 11, I'm almost ready to see the light come on. All I need to do is complete the circuit by connecting this wire to ground, to 0 volts. So let's give that a try. And sure enough, the light comes on. So,
okay. So then I do another one from row 11 to, he said 0 volts, which is ground, right? Oh yeah, ground. I did it! Yay! I made a circuit with a breadboard. So yeah, this is exactly what I did with my Flamingula, but I hadn't known about breadboard. I learned about breadboards later when I was trying to make a more complicated circuit and started running into trouble, and it got very frustrating, and I looked it up and I was like, oh, is that what those little white boards are that I see everywhere? Whoops.
Oh, that's pretty exciting. We've now figured out how to turn the lights on.
Yay!
When I have a complete circuit from 0 volts, or rather from 5 volts to 0 volts, passing through the resistor and through the LED, I am producing light. So that's progress, but now what we'd like to do is get the Hero involved in an intelligent way. We'd like the Hero to take over the job of connecting and disconnecting the voltage to our circuit. And so that's our next step right now. So we will, for the moment, disconnect our circuit.
Okay.
And shift our attention for the moment to the Hero and how we can control the Hero. Now, what we have, I will direct your attention next to our code window.
Right.
What you see here is that the code that is illustrated in this window has a particular sort of structure to it, a sort of syntax to it. What we'll find is that the code that's understood by the Hero consists of statements, and generally speaking, a statement ends with a semicolon, and that's how you can recognize it. And you can group sequences of statements together inside these curly brackets. And so you'll notice I have one routine here called setup with curly brackets, and another routine here called loop, also enclosed in curly brackets. But there's not much inside those curly brackets yet. So our job is going to be to put some statements inside that will actually command the Hero to do something interesting. In our case, what we want to command the Hero to do is to provide voltage to particular locations on the Hero board. All right, so let's get started with some code. The first thing that we need to do is we need to define a variable. And in order to do that, I'm going to put a preliminary statement up at the top of this code window. And the preliminary statement is defining a variable called light. This is just a number, an integer, and I've chosen to give light the value of 12. INT here means that it's an integer, a counting number, and its name is light, and its value is 12. Now, I want you to notice that when the semicolon is typed here, that's the end of the statement. And that's as far as the computer, the Hero, will interpret it. But there's something after the semicolon that's fairly important, and that is anytime you see 2 slashes followed by some text, that's a comment. Being a comment, it's ignored by the hero. But it's not ignored by any human being, yourself included, who's trying to read this code and understand what it's doing. So you should be getting into the habit of writing useful comments whenever you write code, because it will be a very helpful way of telling someone else what you're trying to do with your code, or it may be a helpful reminder to yourself when you come back later and try to remember what you were doing. So keep in mind that comments are very important, and we'll try to use those comments as much as possible. All right, so right now, light is a synonym for the number 12. And our comment tells us that this is going to refer to pin number 12 on the hero, so that we don't have to keep remembering that it's 12. We'll just remember that its name is light, and that's a synonym for it. All right, so let's move on. The two routines, setup and loop, have different purposes or different functions. Setup runs once, and as its name indicates, its purpose is to set up the hero, to get started on its job. And so it only executes once. Whereas loop, which we'll get to in a little while, is designed to run repeatedly over and over again, and will not stop until you turn the hero off. So let's get started by putting some statements into setup. What I'd like to do is the following. I want to use a command called pin mode.
Thanks for the follow, Ryan.
And type pin mode in so that we have an idea what it looks like. Pin mode takes as its first input right here a variable, in this case light. So we know that we're telling pin mode, I want to do something with pin number 12, another name for light. And then it has a function right here. And the function that I want to apply to pin number 12 is to make it an output.
So I can just copy and paste.
Is that with pin 12, you're going to be asked to change its status.
I wasn't listening.
Light. So we know that we're, and will not stop until you turn the hero off. So let's get started by putting some statements into setup. What I'd like to do is the following. I want to use a command called pin mode. And let's go ahead and type pin mode in so that we have an idea what it looks like. Pin mode takes as its first input right here a variable, in this case light. So we know that we're telling pin mode, I want to do something with pin number 12, another name for light. And then it has a function right here. And the function that I want to apply to pin number 12 is to make it an output. And what that means to the hero is that with pin 12, you're going to be asked to change its status, to do things to it, to make its voltage be high or make its voltage be low. So this is what pin mode does, is it assigns a function to pin number light, or pin number 12.
Got it.
Following the pin mode and its semicolon is another statement, digital write. Digital write now does something to that pin, in this case pin 12. And what it says is, set its voltage to low. Low is just another way of saying 0 volts. So when we see high, we're going to see
the copy
high
was
volts.
high.
And when we see low, we're going to have 0 volts. Now actually, since we'd like to turn the LED on, let's change from low
that's why.
to high.
Okay.
That way, when this is executed, pin 12 will now be at 5 volts, and that could be very useful to us. So let's go ahead and see if it works. Let's come back over to our circuit. And instead of taking our wire here and connecting row number 6 to 5 volts, which would turn the light on, let's connect it instead to pin number 12. So pin number 12 is right here. And not surprisingly, nothing's happening. The light's not on. And the reason why the light is not on is right now, since we have not run any code, pin 12 has no assigned function to it.
I was wondering what he meant by pin 12.
And upload our code to the hero and see what happens.
Okay.
So we upload our code, and the light comes on. So we now succeeded in turning on the light, but without actually touching the circuit. We've allowed the hero to do that.
Hold on.
Change this.
I've done something wrong. It's asking me to save sketch folder as... Okay, do I have to save it first? Hold on. I might have changed something. Light was not declared in the scope. Oh, I've already got errors. Light was not declared in the scope. Hold on, let me, going to copy and paste this because I just typed it before and maybe I got something wrong. Oh, maybe I didn't use caps. Yeah, I bet that was it. Because I copied and pasted for the second one, which used a capital L. Oh, it's on now. My hand was in the way. Yay! Okay, so yeah, I guess capital letters are important in C++. It's an important lesson.
Status if we want. If we change the code from saying voltage high to voltage low, or 0 volts, we should now have no current flowing. And so if I upload the code now, the LED goes off. So that's good progress. We've now succeeded not only in turning on the LED, but controlling the LED being on or off by giving commands through the hero. Now, that's interesting, but we haven't even touched the loop function yet. And that is going to be very interesting for us because the loop function allows us to do things repeatedly. So let's see if we can't do something a little more interesting by putting some statements into the loop function to be executed repeatedly. All right, so I'm going to use digital write again, but I'm also going to use a new function, and you'll see what that function is in just a moment here when you take the code and we paste it in. You'll notice, by the way, while I'm doing this, that we did have an appropriate comment in setup. We said that we are initializing the digital pin, in this case pin 12, and set its value to high. Now, what we're going to do in loop is we're going to change the status. And we're going to do this repeatedly as long as the hero is turned on.
I don't get given this code. Why? Hold on. Is there some place? Does that? I don't know what that does. So I just have to type this one in myself, I guess.
And paste it in. You'll notice, by the way, while I'm doing this, that we did have an appropriate comment in setup. We said that we are initializing the digital pin, in this case pin 12, and set its value to high. Now, what we're going to do in loop is we're going to change the status, and we're going to do this repeatedly as long as the hero is turned on. So the first statement in loop does something that might seem a little pointless, and that is it says, change the value of light to 0 volts, to low. Well, it's already off, so it might seem like a sort of a pointless thing to do. But stay with me, because what we're going to do in our next statement is execute something called delay. Delay simply waits for a specified period of time. In this case, it waits for 1,000 milliseconds. And since a millisecond is 1,000th of a second, this waits for 1 second. And then it goes on to the next statement, which is digital write, turn the light to high.
I did it!
And so this will turn the light on after 1 second. Now, there's another delay for 500 milliseconds.
Maximum buggage.
1/2 of a second. And then this whole sequence will just repeat. So if you think about it now for a moment, when I run this, what it should do is wait for 1 second, then turn the light on, leave the light on for 1/2 a second.
I'm a programmer.
Turn the light off again, and do that repeatedly, blinking the light on and off. Off for 1 second, on for 1/2 a second. So let's check and see if when we upload our code, if it functions in the way we expect it to.
It does.
Right now we can see there's no light on. Let's upload our new code, and once it starts to execute, we have off for a second, on for 1/2 a second.
Yay!
On, off. So that's just what we were trying to accomplish. And you can see that we can customize this in any way that we might like. So for example, we might say, well, you know what I'd really like is I'd like the light to be off for 2 seconds. And so I could do that by simply changing the value that I sent to delay to 2,000. So that would be 2 seconds. And then I might say, I really only want the light to flash for a brief period of time. So let's change it to 1/10 of a second, or 100 milliseconds. Okay, so that's my new code. So if I re-upload that to the hero, it should change the rate of flashing. Let's see if that works. Okay, upload, and
I did it!
Here we go. 2 second wait, 1/10 of a second flash. Well, I think you can see now how we are able to use the digital controls of the hero to control our analog circuit and do something mildly interesting with the lights here, flashing them on and off in a specified pattern. And if you wanted, you could probably experiment a little bit on your own. You might be able to write yourself some code that will flash out a message in Morse code, or do something else that might be interesting in terms of turning the lights on and off in some specified way.
I mean,
but for now, we've
I should put out an SOS
and work out the basics of both an analog circuit and its digital control, and that's just exactly what we wanted to do in this session. So for now, you can go ahead and practice with this, and we'll sign off for now. And next time, we'll see if we can do something even more interesting using our breadboard and our hero controller. So for now, remember, invent safe. We'll see you next time.
Yay! Pretty exciting. I'm not kidding about that. I actually do find this very exciting. Yeah. Like, okay, so the guy, he should have hired someone. He should have hired an actor. But I'm enjoying this quite a bit. In fact, maybe we'll just move on to day 2, because that was only a half an hour. Or day 3, I mean. How long is this? It's another half an hour. Yeah, I think I'm ready. I think I'm ready for day 3.
Once again from Rescue Shuttle Control. We've noticed in our telemetry that you have succeeded in getting your lights turning on and off.
Mm-hmm.
And so
repeatedly.
That's great news because it means that you're well on your way to getting your systems up and running. We're going to continue working on today's session with learning how to construct circuits and control them with your hero controller. And we're going to build on what we learned in the last session. So today, what we're going to do is try and give you a little more flexibility in controlling your lighting. We've noticed that some of your power levels are dropping, and you need to be able to turn those lights on and off when you don't need them. So, in order to do that, we're going to involve some switching in today's activity. We do have a switch as a part of our discrete complex.
Yeah.
You may have noticed this before. We have this little device.
Yeah, the role playing really comes and goes, which is why I kind of wish he had hired a script writer and an actor to really like drive it home. Also, like, he's not given us instructions on how to best deal with this software. Maybe he will. I don't know. But it's like, do I just delete this now, or?
That take a look at here.
Okay, let me
It's called a dip switch.
Dip switch.
DIP is an acronym. DIP stands for Dual Inline Plastic. And that name is sort of logical. You can see that it is.
Oh wait, there. I do see it.
In a little plastic package. And it has 2 rows of pins in line with one another. So that explains the name Dual Inline Plastic. This particular device is a set of switches. You'll notice that there are actually 3 switches built into one device here.
Oh, they're so tiny.
You could, in principle, use this to control 3 separate circuits. Although today, we're only going to use one of them. Switch number 1, which you'll see is indicated with the 1 on top of the device right here. We'll soon find out that when the switch is flipped from the off to the on position, like so, then the pins on opposite sides in that row are connected and you have a complete circuit. So we're going to use that today.
It's so cute.
Now, the last time we worked with the hero, we basically were controlling outputs. We were asking the hero through the code that we wrote to either switch high voltage or low voltage to a particular pin as an output. We're going to continue with that today, but we're going to add an additional function today. This time, we're going to have the hero not only controlling outputs on certain pins, but we're also going to have it accept input from us.
Are you fact checking him?
The input that it reads on whatever pins we specify will cause the hero to take the actions that we program it to take. So
that does make more sense.
That additional function today, both in terms of the way we build our analog circuit and in terms of the way that we program and write code for the hero. So let's direct our attention for a few moments to our breadboard and Hero and look at some of the circuit building that we need to do today. If you look at the upper part of the breadboard, you'll recognize what looks like a fairly familiar circuit from last time. You'll notice that we
so it looks like I do have to change things around here.
On pin 12, and you'll remember that last time we were able to ask the Hero to connect pin 12 to 5 volts.
I would at least stop it from blinking.
And so from that, we connect to a row on the breadboard. In this case, it happens to be also row 12. Wouldn't have had to be row 12, though. It could be any place we...
Okay, wait. I wasn't paying attention.
A circuit that begins on pin 12, and you remember that last time we were able to ask the Hero to connect pin 12 to 5 volts when commanded. And so from that, we connect to a row on the breadboard. In this case, it happens to be also row 12. Wouldn't have had to be row 12, though. It could be any place we conveniently wanted to build the circuit. From that connection on pin 12, we pass through a current limiting resistor. And you'll remember from our discussion last time that we've chosen the value of this resistor to give an appropriate amount of current to light our LED light bulb. The current after passing through this resistor passes into the positive terminal of the LED lamp, and we've positioned it so that the current will come out of the lamp on row 11, just above there. Now, in order to complete the circuit, we're going to have to provide a return path back to ground. And so this green wire right here takes us around and down to a row on the column, rather, on the breadboard. It's labeled with a blue line here. And then onward from that to ground on the Hero. You might wonder, why didn't we just go directly from row 11 to ground? And we certainly could have done that, but we were anticipating that we're going to need to build another circuit in a little while that will also want to have 0 volts access or ground. And so we've chosen to make this entire blue column right here 0 volts by connecting it to ground on the Hero. And then anytime we want to get 0 volts, we can connect anywhere on that blue
I'm disassociating now.
So far, that looks like a pretty familiar analog circuit to us. And all we need to do is ask the Hero to supply 5 volts to pin 12, and our lamp should go on. Now, what we want to do...
All right, hold on. So I need to internalize this. Okay. Because it changed slightly. Like now we're putting our LED over on this side. I guess just to give us some more room. Okay, and then our resistor is now going between the 12 hold on. Okay, so this goes from here to here. And then this one goes from here to ground. And then on the little LED leg side, we get the resistor. And then wait. Oh, I picked the wrong one because there's no, some of them don't have plugs along the side. Is that okay? This is confusing now. I was doing so well. Like, are these on the side, these red and blue, negative and positive things? I get that they're all connected, but are they connected going across too? They're not. Okay. So it doesn't matter. Like, I don't have to connect this to this on the same row because these aren't actually connected. This just needs to connect to anything on this negative side. Okay. Thank you. Okay, so on the little legs side, we have the resistor, and then another wire that goes from there, and that will go to 12. All right, so we've got from negative to ground. That goes from that to negative. Am I safe to plug this in now? Okay. All right, and then we do another resistor down here. Later, Ryan. Thanks for joining. All right, and this goes from, the resistor goes from negative to wherever. And then, actually, let's go a little further up here. And then our switch, number 1, oh, it goes across. And okay, so there's this ridge in the middle, right? That this resistor is crossing. So is this side not connected to this side naturally? Okay, it is split down the middle. So it's just 5 and 5. Yeah, okay. All right, so then we've got our switch. Thank you. I appreciate you. All right, and then this goes from the number 1 switch to the number 2. Yeah, the number 2 slot, whatever it's called. And then finally, on the other side of the switch, we go from that all the way to SV. Did he explain what S? Oh, 5 volts. It's 5 volts. Oh, I'm an idiot. Did he explain what SV means, you guys? All right, I think I've done that correctly.
In today's exercise is figure out a way of turning the light on and off without having to re-upload the program to the Hero every time. And we're going to do that using this dip switch. Now, you might think that all we want to do is just take the switch and put it in series with the circuit that's carrying current through the lamp. And that would be one way to do it. But we want to have a little more flexibility in the way that we can control this. And so rather than directly interrupting the circuit and the current that's passing through the lamp, we're going to control the Hero by supplying it with an input. So in order to see how we're going to do that, it's time now for us to switch our attention over to the code window and see how we're going to handle this. As we look at the code window, you'll see we have a couple of empty routines here, the setup routine.
Okay, so I do have to delete everything.
To populate with some code. We've also got a variable,
but now LED equals
diode, that has been assigned our traditional value of 12. So when we identify LED as 12, it means that when we set the voltage on that pin high, the light will go on. Now what we're going to need is another variable. And this is going to be a variable that we will use to command the Hero through our switch. And so what we're going to do...
Yeah, he hasn't explained series yet.
Another variable. And we'll name that one switch 1. You'll notice that we have a comment next to this just to remind us that we're setting switch 1 equal to 2, which means that pin 2 will now be the pin on the Hero that we're going to connect to our switch.
Oh.
Now, we have to ask ourselves, well, what are we going to do with that pin 2 that's different from what we did, say, with pin 12?
Oh.
And in order to understand that, we want to see what we're going to do in the subsequent setup and loop functions on our Hero. So the next thing we'll do is place some code in setup and analyze what it's doing. You'll notice that our comment right now says that we're going to set up both an output and an input on the Hero. We are now once again using pin mode. And in the first of these two statements, you'll notice that pin mode is very familiar to us. It's just like we used it last time. We're taking LED, which is 12, and we're setting its function to be an output, so that when we command it, we can cause LED, or 12, to be either high or low. In contrast, we're going to use pin mode to make switch have a function of an input. The Hero is not going to cause input to change. Hero is going to watch that input and take cues from its value. so that when we cause input to change, the hero will take appropriate action. All right, so that's our setup. But now what are we going to do with that? Well, the real action is now going to be taking place in our loop. And so here's where we will see something quite different from what we have done before. So let's go ahead and put a block of new code into loop and talk a little bit about what it's doing. Got a couple of comments here. I'm making note here that within loop we're taking repeated actions, but these are now going to be actions that are based on the status of the value of switch 1. That is the voltage that is being applied to pin 2. Now, the next thing that happens in loop is something new.
The switch is this little red guy.
We're going to apply a conditional test. We're going to ask the hero to check what is the voltage on pin 2, or in other words, switch 1. If digital read of that switch of pin 2 is equal to high, then take the action contained within these curly brackets, which is our usual action of turning on the LED on pin 12. So in other words, set LED to high, so the light will go on. But now, this is a conditional. It's only taking place if switch 1 is high. On the other hand, if it's not high, in other words, if it's low or 0 volts, then set digital write LED to low. In other words, turn the LED
Makes
off.
sense.
So what this means now is that depending upon whether or not switch 1 is high or switch 1 is low, you will either have the LED go on or off, and we can control that. All right. Hopefully that's fairly clear. Our circuit on the breadboard is not quite ready to work with this code yet. We're going to have to set up a way of setting the value of pin 2, or switch 1, to either high or low, depending on what we want. So, what we're going to do, returning over here to the breadboard, is take our dip switch.
I got a little ahead of him.
So that the first of the 3 switches, switch 1, is spanning across the gap here in the breadboard, so that when the switch is in the off position, these rows on the left are not connected with these rows on the right. But for example, if I take the switch and I flip it to on, like so, oops, let's put that switch on. Now you can see our first switch here is lined up with row number 23 on the breadboard. And now there will be a complete connection from the left hand to the right hand side of row 23. If I switch it back to off, then there will be no connection.
Got it.
Now, this is part of the progress that we want to make, but the next thing that we have to do is to provide a source of 5 volts that we can either connect or not connect to pin number 2, which is going to be our input to the hero. So here I have a long wire that I connected to 5 volts on the hero. I'm going to bring it over here and connect it up to the right-hand side of row 23, like so. Now, with the switch in the off position, that's not going anywhere. There's no completed circuit. And the left-hand side of row 23 is still at an indeterminate voltage level. On the other hand, if I were to switch this to on, the current can now flow through the switch, through this second resistor and down to ground. You'll notice that I'm now using the same convenient ground bus that I'd used earlier on constructing the analog circuit above. So with the switch in this position, I now have a complete circuit, and the voltage on the upper side of this resistor will be at 5 volts relative to 0 volts on ground right here. So if I take this green wire and connect it to pin number 2, which we've named switch 1, now I have a signal that I can send to the hero. When this switch is in the off position, the voltage on this green wire, and therefore on pin 2, is 0. And when the switch is in the on position...
Hi, Don Pedro.
So,
I'm learning
the
switches.
on the green wire, and which is sent to pin 2, is high, or 5 volts. And so the hero will be able to read that input and take appropriate actions on pin 12 and turn the LED on or off.
By the way, there's a detail of our switch circuit that may bear a little explaining. And so let's dive into it in a little bit more detail. You may be wondering why we need to have a resistor between the switch and the hero board.
I was wondering that.
And perhaps the best way of explaining is to examine what would happen if we didn't have that resistor. So I'll direct your attention to this diagram. It shows us what the circuit would look like if we tried to connect and disconnect 5 volts to our hero input with just a switch. So what we have here right now is a diagram that shows the switch in the open position. That is, 5 volts is not connected to the other side of the switch. In this case, you can see that the hero input, our input pin, is connected by wires directly to ground, that is, to 0 volts. And so there's no ambiguity there. The hero should see a signal of 0 volts or low when the switch is open. So that's not too surprising, and it would seem as though this would be a perfectly fine way to wire up the circuit. But now, let's look at what happens if we close the switch. If we close the switch, we now have a sort of a strange situation, because the hero's input is connected by wires both to 0 volts and to 5 volts. So what is the voltage recorded at the hero input? It's really not determinate, because we can't really have this be at 2 different voltages. In fact, if we tried to do this, if we tried to connect 5 volts to ground without any resistor in between, the current that would flow would be huge, probably more than the current that the hero can actually supply. This would be a short circuit, and it has the other undesirable effect of providing or producing a voltage here at the hero input pin, which is indeterminate. We just don't know what it would be. So this would be a poor way to design our circuit. It wouldn't work as we wish it to. So instead, what our solution is place a current limiting resistor, in this case a 220 ohm resistor, between the hero input and ground. You'll notice that in this state, with the switch open, we still have the hero measuring a voltage of 0 volts on its input. We can see that because we can see a path that connects from ground to the hero input. And since there is no current flowing, there is no voltage difference between the two sides of the resistor. It's 0 volts on this side, 0 volts on this side, and so the hero sees 0 volts. Now, unlike in the previous case when there was no resistor, when we close the switch, like so, we now have current flowing from 5 volts to ground through the 220 ohm resistor. The amount of current, if we wanted to know what that would be 5 volts divided by 220 ohms. The important point for us to note now, however, is that since there is a current flowing through this resistor, there's a difference in voltage between this side, which is connected directly to 0 volts or low, and the other side of the resistor, which is connected directly by wires to 5 volts. And we can see that our hero, there's now no ambiguity about what the voltage is on the hero input pin. It's 5 volts. And so we have exactly what we need. That is an input which is 0 volts when the switch is open and 5 volts or high when the switch is closed. And so that, in a nutshell, is why we want to design our switch circuit with a resistor.
I kind of get that.
So with that,
I might need to
go ahead and try
watch this one again.
Our code.
and see if this will work as we designed it to. So we have our code constructed. Let's go ahead and upload it to the hero. We would not expect anything to happen immediately because as we've set things up right now, the voltage on pin 2 is 0. It's low. And so that means that when we get to the conditional test, it's going to the second of the two choices, which is turn the LED off. So let's see what happens now if we take our switch and flip it to on. And there we go. We have now succeeded in remotely activating the circuit that illuminates the LED by providing signal input into pin 2 of the hero. So this is yet another useful way of indirectly controlling the function of an analog circuit.
All right.
In this case,
I
what
fucked
we have
something
the
up.
hero do is make a decision based on inputs provided to its input pin. So that's a pretty helpful additional capability.
My first
that we can
failure.
now, work into our subsequent projects and designs. If you were so inclined, you could elaborate on this and do some additional changes, make some additional functions if you wanted. For example, all we've done right here.
All right, we're going to have to take another look at things. I am thankful, though, that that the breadboard exists and I didn't have to solder any of this. Oh, my LED might be spun around. I guess this means this is the longer foot, right? Oh, I did it. It's blinking for some reason, which doesn't seem... Oh, wait, no. His code does have a blink to it. All right, that was the problem. I had my LED spun around. Yeah, no, his new code does have it has this blinkiness in it. I just wasn't paying attention. Yay! I fixed it. I troubleshot.
Here is simply caused the flipping of the switch to turn the light on and off, which is almost indistinguishable from if I were to just put the switch directly into the circuit itself. I could do something a little bit more interesting. If, for example, I took the code that is executed here when the if statement is true, that is when switch 1 is high. If I replaced that digital...
This was... My issue was copying and pasting what he's included here, but he should really have, like... Okay, if you're going to copy and paste first, do this and then this.
Right.
Okay.
With a series of commands, similar to those that we saw in our last session. So instead of just a single digital write, let's try this and figure out what it's doing. It's saying digital write LED low, wait for a second. Digital write LED high, wait for a tenth of a second. Low, wait for a tenth of a second.
I really thought something had gone terribly wrong.
And then repeat. So it looks like what we're going to have now when we flip the switch on is a flashing sequence where first we'll have the LED off for a second, then on for a tenth of a second, off for a tenth of a second, on again for a tenth of a second, and then repeat. So it'll be a double fast flash followed by a long pause. So let's see if that works.
It does.
Go ahead and re-upload our code.
It works. I have
Once
verified.
again, there's nothing happening until we flip our dip switch into the on position.
Dip switch.
And when we do that, we now have a function
Yay!
that we can control with a single flip of the switch, which will execute a more complicated sequence of flashes. So you can try doing some of your own experiments and modifications of this kind as you get used to controlling your lights, conserving your battery power, we hope, and start looking into some of the other parts of your rescue shuttle that are perhaps dark right now. And as we get more of the lights turned on and more of our functions going,
He's back to the role play.
Tackle some more challenging problems. The next time, I think we're going to try and control more than just a single circuit and try our hand at doing something even a little bit more complex.
Ooh.
So go ahead and work on that. We'll continue watching telemetry here from Rescue Shuttle Control. And until next time, when we have our next session together, remember, invent safe.
He's even got a tagline now. Fun. Fun. Okay, I was a little worried there when it didn't work at first, but no, the fix was pretty simple. Just had my little LED spun around. But yeah, this is good. This is the first time that I've learned something a little new in terms of making the circuit more complex. Oh, wait. Oh, I see. It just automatically goes to the next one. It really is an odd mix. Hey, Pesco, how are you? Yeah, which is why I kind of want to volunteer my script writing abilities. And you know what? I'll even act. Hello, traveler. Just so. I'm doing all right. Getting back into the streaming thing, as you can see, and learning. Learning is fun. Yeah, this is it's definitely a flawed course, but I'm sorry, Besco. Yeah. A filter, something. Like, I think we can improve the production quality of this. But let me see if I can make it through the course first. Yeah. It's a great idea. It's just that their commitment to it isn't great. Ah, good to know, Besco. Yeah, well, I'm learning. Hopefully by the end of this, I should know enough that I can do the improvements I had wanted to do this past year on Flamingula. Because I wanted to make it so that Flamingula's eyes would light up at dusk automatically. Because right now, I have to, go outside and turn his lights on and off. But I picked up a light sensor, and I was trying to in fact, it might be in here, my old notes. Oh yeah, actually I'm using an old bullet journal, and I've got my old notes from when I tried to make that happen, but I didn't, I wasn't able to get it to work, and that's when I was like, fuck, I should be doing this on a breadboard. But then I didn't have the energy left to figure out how breadboards work. Yeah, I think so too, Empty. I don't know. Something went wrong in terms of, it might have been a similar problem actually. I just had the LED reversed or something, but because I was doing everything by soldering it together, I was just like, oh, fuck this. So, yeah. Hopefully, I can figure that out. But yeah, I just want to have a solid handle on what I'm doing. It's hard for me to get my brain around this stuff. So, I would like, if I learn more than I need, it'll be easier for me to go back and do the stuff that I need to do for it'll be easier for me to do the simpler stuff, you know what I'm saying, right, Indy? You know what I'm saying? Know what I'm saying? Sit. Good boy. Shake. Shake. No, sit. Shake. Shake. No, it's not back up. Sit. Good boy. Shake. Shake. Yeah, shake. No, it's not back up. Shake. Shake. Oh my god. He learned one trick and it pushed another trick out of his little tiny brain. Sit. Good boy. Shake. Shake. Good boy. Yeah. All right, guys. I'm going to take him on a walk. Thanks for joining me. I hope you guys are enjoying the new game we're playing. Because I'll be back doing it tomorrow. Yeah, sorry, Besco. 2 p.m. You got to be here at 2 p.m. And the streams are shorter now as I get back into the fun. So yeah, I'll be back at 2 p.m. tomorrow. Thank you for all your help, guys. All right. Have a good night.